Sample exam 5, problem number 10. A rectangle is to be constructed having dimensions x by 2x, where x is a random variable with density function f of x is equal to x over 2, where x is between 0 and 2. What is the expected area of the rectangle? Sample exam 5 of 8, problem number 10. We want to find the expected area of a rectangle with sides x and 2x. And so the area is 2x squared. So we want to find the expected value of 2x squared. So we plug that. They give us the density and our domain. Plug it in, integrate it, plug in our limits. The answer is 4. Number 11. A manufacturing firm needs to test the null hypothesis that the probability P of a defective item is 0.1 or less, against the alternative that P is greater than 0.1. The procedure is to select 2 items at random. If both are defective, H0 is rejected. Otherwise, a third item is selected. If the third item is defective, H0 is rejected. In all other cases, H0 is accepted. What is the power of the test in terms of P? Number 11, we reject if both observations are defective, and if not, we take one more, and if it's defective, then we reject and say that the lot is defective. We're going to solve this 2 different ways. The first way is we reject if x1 is 2, regardless of what happens. If x1, our first sample is 2, reject. Else, if our sample yields 0 defective and the second sample is defective, then we reject. And also, if the first sample is 1 and the second sample is defective, we reject. So these are all, x1 and x2 are independent. So the probability that both are defective is p times p. Here, 2 items both not defective is 1 minus p squared. Defective. The probability that 1 is defective is 2 times 1 minus p times p, and then that is p. And then this simplifies to this, which is the answer. Now the second case is where I like to draw a graph or a picture of what's going on. And here we have 2 variables, x1, which is the first time we sample, and the number of defectives can be 0, 1, or 2. And then the second sample is of size 1. The number of defectives can be 0 or 1. And the circles here, the thick circles, is the first time we sample. If we get a 2, we reject. And the second time we sample is if we get a 1 on x2, we reject. So we just need to find the probabilities of these dots and x's. And so if we look at the probability that x1 is 2, which is this case, the probability that x1 is 1 is this case, but we counted that one twice, so we subtract the probability that x1 is 2 and x1 is 1. Well, that's p squared. This is p. And then this is p squared times p, which is the answer. Number 12. A random variable has density function f of x, 0.4 between 0 and 1, 0.6 between 1 and 2, and 0 otherwise. Which of the following statements about the random variable x are true? So number 12, it's asking us, is the distribution, is it continuous, is it discrete, is it mixture, what's the probability? And to determine if something is continuous or discrete, in statistics, or probability in statistics, that's in terms of the cumulative distribution function. So looking at a PDF, probability density function, you can't always tell if it's continuous or mixed. Here it looks like there's some jumps, so maybe it's discrete, and then there's some continuous pieces, so maybe it's continuous. So by this you can't really tell. Now there is a way you can tell by looking at it to see if it's what's called left continuous, but we won't get into that here. We're just going to look at the CDF, or the cumulative distribution function. So if we go from infinity to x of our density, d of x, now if it's less than 0, now pretty key to this, and includes 0, it's 0. And then when we integrate this function, which they provide, over 0 to 1, it's 0.4x, so it kind of increases. Now another note is that the equal sign is here, it's equal to 1. And then over the third range, from 1 to 2, this ends up being the CDF. And again, the equal to is on 2, and 1 greater than 2. So if we plot this, it looks like this. So this this distribution, or the cumulative distribution function, is both right and left continuous. So this is a continuous function. Another way to think about it is that the probability of a single point is always 0. And that can be defined in terms of the cumulative distribution function. So the probability that x is equal to x is the CDF of x minus the CDF of x minus a little epsilon. And then you let epsilon go to 0. And if that is 0, then, you know, for every point in here, then we know it's continuous. And this also plays a part that this is left continuous. But now let's look at the probability that we're between 1 and 2. Now, the problem gives, you know, it's an equal to sign here. But we just showed that any point, the probability is 0. So it doesn't matter if there's equal signs or not, because this is a continuous distribution. So we can simply take f of 2 minus f of 1, which ends up being 0.6. Problem number 13. Suppose that x1 through x6 and y1 through y9 are independent, identically distributed normal random variables, each with mean 0 and variance sigma squared. What is the 95th percentile of this sum of the xi squared divided by the sum of the yi squareds? Problem 13. We want to find the 95th quantile, or such that the probability that this is less than some number p is 0.95. Well, this looks, each one of these are kind of is the beginning of a chi-squared. Now, x and y are independent because that's given in the problem. And whenever you're showing something as an F distribution, the numerator and denominators have to be independent. Now notice that the xi, if we take xi minus the mean, which is 0, and square it, and then divide by its standard deviation, which is sigma, and we do that for the denominator, yi minus the mean of 0 squared divided by the standard deviation with the sigmas cancel from the numerator and denominator. And so now the only thing that's stopping this from being an F distribution is that we have to divide by the degrees of freedom. Well, the degrees of freedom in the numerator is 6, and the degrees of freedom in the denominator is 9. And now one point of confusion is, why is it sometimes we divide by n minus 1 and then sometimes we divide by n? Well, when you're taking xi minus the sample mean quantity squared, then we have to divide by n minus 1 because of the degrees of freedom associated with n minus 1. Here we know the mean. The mean is 0. The true mean is 0. So the degrees of freedom is 6 and 9 in this case. But if we divide, and if we do it to the left side, we have to do it to the right side. Well, then this left side is an f with 6 and 9 degrees of freedom. And we want this probability to be 0.9, which implies that this piece here is 0.37, which implies p is 0.12. Problem number 14. Suppose the random variable x has moment generating function m of t, which is equal to 1 minus beta t raised to the minus k, provided that t is less than 1 over beta. What is the expected value of n? So number 14, we're given the moment generating function, and then we're asked to find the expected value of x raised to the n. So to do that, we need the nth derivative of the moment generated function associated with t and then evaluate it at 0. So what you have to do is start taking derivatives and hopefully you find a pattern. And so the first derivative of the moment generated function is this. So it's beta k and then minus k plus 1. The second derivative is beta squared times k plus 1 and then subtract k minus 2. So if we were to continue this, then the third derivative would be a 3 and that would be a 3, and then we would multiply up to something k minus 1 less than 3. Well, and then you can show that the nth derivative is this, and then to take the expected value of n, x to the n, we want the nth derivative, which is this, evaluated at 0. So plug in 0 for this t, and then 0 times beta is 0, and then so we're left with 1 raised to a power, which is just 1. So we're left with this piece over here, and then that's the expected value of x to the n. Suppose that x1 through xn are random variables with expectation 0 and variance 1 for I equals 1, 2, 3, and the covariance of xi and xj is equal to minus 0.5 when I is not equal to j. What is the variance of y, which is the sum from 1 to 3 of I times xi? Now number 15, we want to find the variance of this sum. So we take the variance of xi, x1, x2, x3 with, don't forget about the 1 in front, which is what this piece represents. And then we take the covariance of each of the combinations. So in this sum, it ends up being we take the covariance of x1 and 2x2, but then it also is the covariance of 2x2 and x1, but that's the same, so that's why we end up putting a 2 out front and we just have one of those. So we take each possibility, times 2, and then we're given the variances and we're given the covariances. Now remember, constants come out front squared in the variance, so the 2 becomes a 4, the 3 becomes a 9, but in the covariance, constants just come out times. So, and I think of this in terms of matrices, and so this one, the constant comes out this way and this one comes out backwards. But since this is scalar, it's like they both can come out front. So 2 times 2 And then here is 1 times 3, which is that piece here. And then 2 times 3 is 6, which is this piece. Multiply it out, you get 3. Problem 16. A fair coin is tossed until a head appears. Given that the first head appeared on an even number toss, what is the conditional probability that the head appeared on the fourth toss? So problem 16, we're tossing a fair coin, and we're given that the head ended on an even toss. And what's the probability that it ended on the fourth? So this is our density of a win, or until a head appears. So the last one's a head, and then all the previous are tails. Well, in this case, since the probability is 1/2, those combine to 1/2 to the x. So the probability that head appears on an even is it's 1/2 squared to the 4 to the 6, etc. Now we're going to take 2 of those, the squared, and bring it in, and we get this. So if 6 is 2 times 3, so you take the 2, you make it to the fourth, and you have a 3 left over. And the reason I do that, because now this expression looks like a geometric. And since the first term is 1/4, that's what you start with, and then it's always 1 minus this number here, which is less than 1, and then you get 1/3. So the probability that x is equal to 4, given that x is even, is this. Well, the probability that it's on the fourth is 1/2 to the fourth, and we just showed that this is 1/3. So you multiply it out, you get 3/16. Problem number 17. Suppose 2 independent populations have Poisson distributions with parameters lambda1 and lambda2 respectively. x1 through xn and y1 through ym are random samples from the 2 respective populations. Then what is the form of the best Neyman-Pearson test for testing the null hypothesis that lambda1 is equal to lambda2 is equal to 1 against the alternative hypothesis that lambda1 is 0.5 and lambda2 is 2? In problem number 17, we want to test the Neyman-Pearson that the lambda1 and lambda2 are equal to 1 against the alternative that lambda1 is 1/2 and lambda2 is 2. And we're given data x1 through xn, and each are Poisson. So the joint density for the x's is this, where n is from 1 to n, this sum is from 1 to n, and we're given the y's where 1 to m, so the joint is this. And then to find the joint of the x's and the y's, since they're independent, you just multiply these two together. So then to find the rejection region, Neyman-Pearson rejection region, we set up the joint density under the null, and then I just did it in terms of x's and forgot to write the y's, so it's crooked, but and then if this is too small, meaning less than some constant, then we reject. And then this is the probability of that happening, you want to be alpha. But all right, so we take these two joints and plug in that they're the lambda parameters are 1, and then this times this, when lambda is 1, we get this, and then this times this under the alternative hypothesis that lambda is 1/2 and 2, we get this. Then we start simplifying and taking any constant, and constant in this term means doesn't involve an x or a y. So these products here, the factorials, cancel. And then this is not a constant in regards to x and y, so that can go to the other side. this is not a constant, so it can go the other side, and we're left with this. So, and this is in the denominator, so let's take them to the numerator, which makes this exponent go negative, and that's what we get here. And so it's less than some constant, and this constant is c times a bunch of these constants. Then we're going to make this a 2, which we take it up, and it's 2 to the minus 1, but that minus 1 can be brought in here to make it a positive. We have like bases, we get this. If we take log base 2 to both sides, this goes away, and then we have this sum less than some constant. And that's the Neyman-Pearson rejection region. Number 18. 2 balls are dropped in such a way that each ball is equally likely to fall into any one of 4 holes. Both balls may fall into the same hole. Let X denote the number of unoccupied holes at the end of the experiment. What is the moment generating function of X? So number 4, I kind of messed up here. I let X be the number of holes with balls. Now in the problem it says let X be the number of unoccupied holes. So I redefine, I let Y be the number of unoccupied. But we'll go through how I solve this. Because the way I like to think about it is it's easier for me to think about how many holes have a ball. So then the number of possibilities to put 2 balls in 4 holes is 16. There's 16 ways. So our denominator is going to be 16. And then there is, if you take 2 balls and then you pick a hole at random, then there's 4 ways to do that. Then the second ball has to go in that same hole, so there's only one possibility. So the number of ways that we can have 1 hole occupied is 1/4. So then the number of ways that we can have 2 holes occupied is, remember there's 16 total ways. So if we pick one of the holes at random, there's 4 ways to choose that. And then we need to pick one of the other 3, and there's 3 ways to do that. So it's 12 over 16, or 3/4. Now this is X is the number of holes. So to define the number of unoccupied holes, we let Y be 4 minus X. And then, so the probability that Y is 3 is the same as the probability that X is 1 is 1/4. And you don't really need to do these steps. That's just kind of the way my brain works for this problem. And then the probability that there's 2 unoccupied is the same as there's 2 occupied, so the probability is 3/4. And then the expected value is just, it's a Laplace transform of expected value of e to the yt. So you plug in this, and then you sum it over the probabilities of each of those y's happening. And when I is 2, which is here, so we get 3/4 e to the 2t, and then when I is 3, then it's 1/4 e to the 3t, and then that simplifies to 1/4 times 3 e to 2t plus e to the 3t. Hope you enjoyed the video. Please subscribe so you don't miss any of the other questions and answers coming your way. Thank you. Bye.